I think anybody who wants to come is already here. Fair.
Did you start the stream?
Yes, I did start the streaming. And as usual, we have this helper tool to make our lives easier when we change code and to get updates live. Fair bit of warning. Turn your earphones down. Otherwise, you will destroy your ears in the process of coding. It's painful. Anyways, we're going to start with the most boring part. There's a tiny library included in the whole system to help us build UIs and kind of control boxes and kind of slider thingies, so we don't have to worry about those and code ourselves. So you can see that it's mostly that we define an object to what are the different parameters, and then we say that, oh yeah, I want some slider for it as well. For example, here we say that I want a slider for this control object named volume and from 0 to 1 range. So we'll get this volume thing here. Anyways, we can go on to our first example. Then, if you don't have any questions about this thing here, this UI building, that's not the important part. So the first thing is we'll open up the noise example, and now when you turn up this, you should hear some noise. And I'll go through the whole code example as well, but now set your earphones such that when you turn up the gain, it doesn't hurt. So when it's at 1, you should be fairly comfortable hearing it. Otherwise, you might get sounds louder than that during the programming. First, how does audio work? So let's say we have a speaker here. Let's draw it this way. It's a speaker, and here's a membrane that moves up and down. This generates pressure waves essentially, and this we interpret as sound. So what do we have to do to create sound from the computer is we need to drive this this speaker with some device. Usually this is our audio card. Some device. And now the question is, how do we get the signal that we want the speaker to make? How do we get it into the audio card? Usually this is done using some sort of buffering. You say that, oh, I want to create I want to create this much sound, and then we will fill this buffer with some values, and then say to the audio card, oh, please play this. This is how essentially we get these different values and speaker positions that we say that, oh yeah, create this power output from the audio card to the speaker, and then the speaker vibrates, and then you will get sound. In practice, what it looks like, how to set it up. For the browser, we use an audio context to say that, oh yeah, we want to do something with audio. I'll make it bigger. Then we say that this buffer size is, oh yeah, I want to send this amount of data to the audio card at the time. So this is the buffer size. And then we say that how many speakers we actually have, like maybe we want to do stereo audio or like mono audio or something. And then we set up something that can, we can remove this from here. We set up something that can generate the audio for us. So here we just say that, oh yeah, we have this buffer now here. This is this thing here, like this thing here is this data, this thing here. And we go sample by sample, or each like small slice of time. We say that, oh, I want to have this exact volume there. So it might look like, so we have these little boxes where we say that, oh yeah, here should be -1, here should be 1, here should be 0.5. So this is the audio buffer. And here we put something random here. The values for any audio output usually is from -1 to 1, depending on where you're using it. For some like smaller embedded devices, it might be from 0 to 256 or something. But essentially, here we generate, put some random stuff in it, and this is what we hear is this thing here. So this is when we just fill it with random stuff. And currently, this is kind of really hard to interpret because, or see what's going on. Otherwise, we'll be like, the whole workshop will be staring at a blank page. So instead, I have this thing here, which is the second example. Effectively, I've removed all the setup code from there and just left the processing part of generating the single audio buffer. And what you can see here, we still generate the white noise here. What you can start playing with the numbers and kind of different things here. As usual, like you might put -2 here and kind of try to experiment with different things while we're doing things. And feel free to ask if you want something. So you can see here we can resume and pause the rendering, and this is what gets sent to the audio device. So we can see that we have here these random points, essentially a random line that the driver makes. And here, this section here is the frequency spectrum. This is all the different frequencies we can hear in the sound example. So usually human hearing ends about here, like, what was it? Yeah, something like that. So about here, about that we cannot hear. And this is essentially the whole setup that we'll be using to see what's going on in the system. And one thing you can see that when we modify the gain here, you should see how it changes also in the output. One of those things that you should notice here is that when you slowly move this slider up, you hear that it doesn't get smoothly louder, but instead there's like a curve there. So when you play with this gain, because here it doesn't do much, and here it changes quite a lot. kind of. So this means that there's a difference between the amount amplitude that we send to the speaker and the value that we want to say that, oh, this is this loud. So in the next example, when you go in the tree, there's this way to get convert this logarithmic scale back into linear scale, so we get this smooth transition for the audio output. This means it's just more convenient to control, but the important thing is here that often these different values aren't linear scale but logarithmic and power scales and kind of. So we may need to do some mathematics to generate this. So now that we have something like working this noise, we might start to wonder, what if we generated the noise some other way? So by the way, this is called white noise. So we can take the example brown. This is the brown noise, and you should hear that it's the timbre is kind of like much lower. Yep. So you can. So you may need to put the volume a little bit up. Remember to turn it down afterwards. But here, instead of saying that, oh, we'll put just random value in the output, we'll use a moving average. So what we can, instead of saying that, no, where did you go? So instead of saying that, oh yeah, let's put some random stuff, we use this Brownian motion, which means that we have this moving average which moves a little bit up and down. So this will generate the lower tone and kind of give some other sound. So effectively, what we will be doing is we'll be start to examine different ways of producing these values to generate different sounds. And I suggest trying to know what's happening, to change these values here, to experiment what happens. So, and be careful, because something like this might happen, and say like so. And if you're adventurous, you might want to try something already like put the sinus function somewhere. Try what happens. Let's say something like let's plus something sinus to see what happens. Currently nothing, or something like this. Yes. So this is what you should be doing. Experiment with things while we're poking them. And finally, for the pink thing, we can also start combining those values, really complicated ways to get much more interesting results, and kind of we can create those sounds in many ways. So experiment with those numbers a little bit. I'll go around, see whether anybody wants to ask questions about the first chapter of noise in general. So, any interesting results? Okay. I think. So. And I guess we can move on now to creating something that doesn't sound like noise. This is the sine wave. Here we have time. So we need to keep track of time to generate the proper sound. And here we can also see the sound wave like really being sound wavy, sine wavy. And we can try changing some numbers here to see what happens. Right? Oh. So we can kind of try different numbers here. Or maybe so and here we can then see how we can now actually keep track of time, because currently remember we are creating this buffer, like this buffer here, let's say, and there's every step here has a time associated, how much time is from one to the next cell. So effectively this quantity, how many of these boxes there are in a second, is called samples per second, or sample rate actually. So rate. This is how many, every time we fill a element here in the buffer, this is how much time advances, essentially, from one to the other. So to keep track of the time that we are, when we are producing the sound, then we need to manually keep track of the time and add those increments every time here. So this is seconds per sample, which we can get from this sample rate. So, for example, sample rate might be like 44,100 hertz. So, or 44,100 samples per second, essentially. And we need this seconds per sample, or how long a single cell is. So this is the inverted sample rate. And then we can use this time to calculate this sinus function to get this nice smooth thing. We need to keep track of time to understand properly this, how to advance the time steps. And so So we can take the second example, because here we don't actually know what we are like producing. We are just putting some random number here. Ideally, we want to say that, oh yeah, I want to hear 440 hertz or something. So there's this frequency example where we can see that we can produce, actually calculate the exact sound to the frequency to play. So if you have absolute pitch, you should know this is A. So you can play with this just for a second. So how do we calculate the exact frequency? Here I have this helper function which converts this time value and frequency into the phase of the sine wave. So when we think about the sine wave, when we speak about producing, for example, 220 hertz, we think of like this circle and this like point going around this circle and doing this 220 times per second. Now that we know that this circle is like 2 pi in length when it's a unit circle, then we can just calculate that, oh yeah, this, when we are doing 220 hertz, on this path we must be at 220 almost hertz times 2 pi and times the time. So then we know exactly at which point we are on the circle. So we are essentially measuring this phase, or how much have we traveled on the circle. So this is the calculation here. So that way we get this proper phase that we need to use in our sine wave. Otherwise, when we just use, for example, time times hertz, it sounds like this, and this isn't even close to an actual note A. So one of the things you should be noticing when you are playing with this frequency is hear this clicking noise. This is our first audio artifact, and when you put it on a pause, you should be able to find it. What's happening? I missed it. Oh, damn it. Maybe you can. Okay. This way it's easier. Oh, here. You see this point here? This is the clicking noise. This is when your speaker jumps from one place to another, essentially, in a very fast pace. So this creates this clicking noise. And why this is happening is that when we multiply this, the amount how much we have traveled on the circle, for example here, let's say we are at this position on the circle, and then we just change this frequency here. Then at a single time point, we will jump, for example, here. So our essentially, let's say at here we jump, and then here's this sharp turn, and then we kind of do this jumping around on the circle, which means we kind of break this sine wave, nice sine wave. So, any ideas what we have to do here? No.
0.2_smooth.js.
Yes. The idea is not to directly use time, but instead keep moving on the circle and keep track where we are on the circle. And then just always increment this step by step. That way we don't get this breaking points. So when you open up the smooth, you should see that there isn't this clicking noise anymore here. And here we do this by keeping track of the phase instead of time. So where we are on the circle. Yes?
Isn't it the same as interpolating between the different frequencies?
No. The interpolation will smoothly start like, how to say? In one case you get like this thing. In the other case you will, do you mean interpolating the frequency or
if I change the GUI, then I don't immediately change the actual frequency I'm using, but I'm feeding towards the target.
It doesn't work on higher frequencies because you will still because the interpolation step needs to get smaller and smaller when you change bigger frequencies or kind of, yeah. So you need to kind of, so technically, yes, you can kind of avoid it, but you might still get these jagged edges because you're still jumping around on the circle. So the solution is that instead of keeping track of time, we calculate how much we have to increment, how much we have to travel on the circle. So here, and then every time we increment this phase with this amount of, we might need to travel on the circle essentially. So, okay, makes sense. So, because it's really boring to use this thing here, we should use the keyboard. So here's an additional helper thingy. It maps your ASDF keys to a piano keyboard essentially, which is not in Estonian. You need to use English keyboard, but so here there's this simple keyboard function that gives you a frequency when you in a callback. So you don't have to calculate this frequency yourself at this point. So, and now we can already have a functioning synth essentially. But one thing real synth needs is like a way to show that it's actually playing, or kind of it's not this single tone like this. This kind of gets boring really fast. So what we might want to consider is to shape the sound. So instead of using a single amplitude, we shape the amplitude. So here we'll use a function to multiply with the output. So let's say I have this let's say I have this sine wave here, and now I want to shape it. So what I can do, I can take another function that's between 1 and 0, and when I multiply these two, I get the sound that's like shaped. So when you look at here, we can see that we can already see this picture that, oh yeah, it's kind of different. So, and when we do this, we get much nicer shape here. And as you might have noticed, we start getting these clicks again. So we're not going to fix this at this point, but the problem is the same. We are breaking this sine wave, like snapping it in two. So, and in the code, I had here different examples. Let's make some room. So I have here different shaping functions. So there's this link here. There's this impulse function that's quite nice to use. Looks like kind of this. This is the first example you'll see. The other is cubic pulse, which is much smoother in shape. And then we have an envelope, which usually means that instead of saying that like a smooth function, we linearly create this function. We have this function that we use. This is called the attack, and this is called the release here. And this is the envelope function. There are multiple forms of this, like that have like shape like this and have more parts to it. And you can probably figure out how to write one. It's kind of figure out that where you need to this based on time, like what is the value here. And you can try try these different functions here. For example, this envelope. Or you can try writing your own function here. And as a final thing, and it's really good because you can actually see the shape that your function is. So yeah. And finally, we don't have to use just one function. We can use many functions to generate the sound. This sine wave is probably the most common, the most basic. You can see here this like really smooth thingy. And when we go to the miscellaneous, there are different functions you can use throughout your code. I have mapped them to number keys, so you can use 1, 2, 3 to change them. In this example, in the miscellaneous. So you can write those functions yourself as well, but here we have the sawtooth, which you can see obviously named for some reason. So, and you should be noticing that when we use the sine wave, we get the pretty concentrated the pulse on the frequency spectrum. The reason that those other sounds sound different is that they have more frequencies mixed in. So sawtooth looks a lot different than a sine wave. So a sine wave, sawtooth, and there are many more. Square wave, you can see how it looks there, and triangle, so, and the noise function. Or you can use some custom combination of all of them. So play with those functions and try to come up with your own sound by adding those different things together and multiplying the phase with some number. And here is the custom example that you should try to manipulate, and you should be able to combine it to get miscellaneous sounds. Questions? When you are experimenting with the custom function with the code, it's useful to set this here to custom, the default value, so it doesn't change every time you save. oscillator ongi üks funktsioon, millega see baasfunktsioon genereerib sulle ehk siis siinus on näiteks üks oscillaator, soolkoht on üks oscillaator. Et see on see baasfunktsioon, et kui sa
Käis nii seal.
See on see oscillaator. See on
Seda vaatab üles ja
kui sa vaatad siis square, et siis tema on sinus, aga siis ta vaatab seda, et kui ta on mingis punktis suurendab
enne seda kuidas see trikib ja mis nagu efekt seda jah, mis ta on, see on nagu väiksem.
jah. See on see kuju. See on see, mis tämbertallane, mis kõlab. Heli.
Auto.
Kus see sõigas seda? Mis see kõige?
Ehk siis nagu see, mis kuju peaks nii on, sellest sõltub see, mida kuuleb. Ehk siis see, kui tihti see asi kordab ennast, see on see, mida sa tegelikult kogusena ja see, mis kuju on see tämber, ehk siis see helispekter, et sellest või selles kujus tekib see helispekter ja siis nagu see, mis on nagu inimene ja muud helid on kõik erinevad. So, I think we can now continue with common audio issues that you might hear in different situations when you start playing with code. So, the first example is that all audio is real time and you cannot escape it. So, here I have this setup that measures how much it took to generate this audio. So it takes like 0.1 milliseconds, but the buffer length that I have to fill is 21 milliseconds. So this means that when I go over this limit, guess what happens? This is what glitching audio sounds like. Because we aren't filling the sound wave properly anymore, and we are getting these small gaps in the audio stream, and we are kind of losing this coherent sound. So you might get this also in when you like refresh the page, you hear also a little bit of clicking. This is also caused by sometimes by this JavaScript doing its own thing, and you cannot fill the buffer in time, and you are missing your frame or the buffer, so you get this different kinds of clicks. So that's just one way how it can glitch. The other way is that we might start to clip at the upper end. So we know that all the values are from -1 to 1, but what if we go over that value? So now we have this good, nice tone. What might happen is we might start getting this clipping. You hear when I like push it like louder, we start to get these higher like noises and frequencies as well. And this is what's essentially called clipping. And it starts to look more like a square wave than regular sine wave. So when you go over your one floating point like number, then you will clip at this edge, and the audio card has nothing else to do than throw that information away and not play it at all. Then we have this really cool problem called aliasing. As we know that when we generate audio, there's a limited amount of information that we can send to the audio card, and this let's see a picture. And at some point, when we try to send too much information, we start to get this problem called aliasing, which looks like this. And when we send each sample, we essentially cannot differentiate between two sine waves. So effectively, one sound that we want to be played sounds like another. So this is the, for example, for like 44,000 kilohertz, the limit arrives at 20 kilohertz. So we cannot play sounds higher than that. So, and what happens when we try to play something higher? This is the scales. You can try it on your computer. Or, even better example, we can take this frequency and start to increase it. We increase the frequency at each time step, so we can see what happens in that frequency spectrum. Okay. So we can see, okay, let's make it faster. We can see it bounces back from there. So this is what our ears hear, although we send us, like, try to generate something else. So this problem is called aliasing. And for some functions it's really noticeable. For example, the sawtooth wave, you hear this all kind of sounds going around because it has so many phase frequencies, or those overtones and kind of that mix up. You might be able to use this as a cool effect, but yeah, this is one issue you might hit. Another one is that we have only limited precision, and some functions just break down when you use too big numbers. So, and at some point this sawtooth breaks because it has been coded badly by me. So you need to kind of, when you're generating a long fade or long audio, then you might hit this problem as well. And finally, because you can actually do pretty cool stuff by removing information from the sound actually. So the Pitify example is where we quantize this sine wave into small steps, and we get this much different sound than a pure sine wave. So this is the sine wave, and when we make it discrete, we get this much different shape of the function and kind of different sound, more 8-bit-ish and kind of cooler, if you think this is cool. And these issues you might hit, whether you like it or not, or want it or not, and hopefully when you hear some of these, you might start recognizing them in other places as well. So
Is it possible to create band-limited oscillators in Java?
If it's possible in any other language, then yes.
Yeah.
So kind of, we are just sending numbers or calculating numbers, and kind of it's possible in JavaScript. So and so now that we have mastered how to create a synth, we want some more effects on it. So here we have a basic setup for like audio graph essentially. We have a single tone that is playing, and each time we call this process function, it gives us a new sample. And we have this neat feature here to switch between noise and sine wave for reasons that will be obvious later. And we also added a small vibrator to the frequency by modulating this. Instead of using a single value as the frequency, we wobble the frequency like up and down within 2 hertz here. So we get this nice sound. So we have this tone object that is capable of producing sound, and here we fill the sound with this noise. Anyways, so what might we want to do with how we might want to process our sounds, or those these buffers that we process? So one idea might immediately that you might get is that, but what if we take the sound that we just generated and put it back into the next buffer? What will happen? So this is the delay example. So, and it sounds like this. We get this kind of reverberation effect. So this echoey stuff sound. And this is without it, and this is with it. And you can play with the numbers here. So what's happening here is that we are creating ourselves an additional buffer. Let me draw what's happening. So to create this effect, what we do is we create ourselves extra buffer. Let's say this is our effect buffer, and this is the buffer that we need to fill. So every time we get this sine wave here, or whatever function we have, we first put a value here, and then we look up a value from here as well, and add those together and use this as a value here. So effectively, every time we get the value from this sine wave, we add it with some previous value. And afterwards, we also copy these values back into this buffer here. So effectively, every time we generate, so this is, let's say, the last generated output, we use, we generate this thing here, we add those together and put it into our output, and then we feed it back into the buffer that we have. Does that make sense? You can say no.
It will later.
No. But so we remember what we played, and we reuse that same sound, and it is obvious that it works, because when you speak, eventually the sound comes back at you from the other end of the room, and then you get this reverb, so you get this feedback. from the row. And this is what's happening here. So okay. So and yeah, it's implementation wise, if you know what a ring buffer is, then yes, this is a ring buffer and it uses that to implement it. Otherwise, we just process each sample and kind of do our normal thing as we process things. One other thing that we might think of is that let's not worry about the whole history that we have done, but instead just use 2 last values. So let me draw here again. Let's make it quiet. So what we can do is, let's say we get this new value s, and we need to want to create an effect. So we can then create this, remember this value here, for example, that we got from the sine function, and then use, let's do it the other way. So this is what we want into the output, and this is the previous value from the last sample. So we can add these together, for example, like let's use 0.1 of this and 0.9 of this for whatever reason, and we get this new value like sample n. What we can now do is that we can output this value and then put this value back here, and we might even consider like adding this into here as well. So what will start happening here is filtering. So when we think about functions, let's say I have this like rising function here. So when I take the previous value I outputted here and multiply this with some particular number and like add it or subtract it, we might get 0 here. So effectively this whole line might become 0. So we eliminate like this sound here. This becomes like let's say something like this, because we subtract like these things that are shaped like this. The other way to think about this is about filtering is, let's say you have a sine wave and you shifted this sine wave this way for some amount of time, and you subtracted these here. So then you would get a 0 here. Of course, when it isn't the same sine wave, we get it through the function. So we filter some of the frequencies at the same time. Some other frequencies either get stronger or lower. So this is filtering in essence. So we manipulate this function to find these different gradients and kind of things to create the different effects. Let me bring back audio somehow. Okay. So let's say I combine things. This essentially means that now I'm calculating this over this function. I'm using this moving average. So this means that I'm filtering all those kind of these bits here and making them smoother. So, and we can of course use the other way. We can see how the frequency changes. It's especially visible in using noise. So we can see how we can manipulate the frequency with just these 2 parameters. by combining and adding them together. For example, here we can see that we have amplified the higher frequencies and lowered the lower frequencies. We can of course do the reverse. Let's use something. Yeah, I don't know. Let's use something like this. So without the filter, with the filter. So, and there's a number 3 that helps you randomize the values to kind of see what might happen when you use different values. So this is filtering. How to exactly calculate these numbers and like the constants there, that's just beyond the scope of this thing and is a whole semester of signal processing. Anyways, and what you might want to do is try to combine these things together, like have this delay buffer and randomly kind of sample different things. For example, the custom example. We of course have some glitching here, which is we get this flanging sound, and in essence we are just using the primitives, using a buffer where we store the last values, and then we sample from the buffer using some sine function or something, and this is how different effects are made. It's fun to play around, but to get something real production quality, it's just quite a lot of pain. Okay. And of course, we can combine these effects or like pre-processing of buffers directly into the tone generation. One really good example of is Karplus strong algorithm, which creates us a guitar sound. So here we generate the random a buffer of random values, and then start attenuating it or like decreasing the values slowly there. So you get this guitar sound. Let's use. Or if you want, you can tweak the parameters to look different. Hardcore guitar. Or a kind of saw. Oh, I know what would be good here. Let's make it lower. Or so you can change this thing here. So this is the place we get the frequency value from the keyboard. Or let's divide it by, I don't know. So, and of course, there are different existing algorithms to create proper filters and effects. If you're interested, you can implement them yourselves. I wouldn't recommend it because it's just pain and a lot of work to get them correct and not to get those glitches and issues that we have listened before. So you can now play with those effects. See, pick one effect that you thought was cool, and you can play around with the numbers, add some sinus functions in some places, and kind of add some noise into some place and kind of see what happens.
Just make myself an alarm.
Oh, one thing you should also try is try to switch out the base functions if you're using some effect. You might change the saw to some sine function or square function, or you can see those in the miscellaneous code what the functions are called. So. Liigugu vast?
Ei, liiga, ma ei tea, mis teeb kõrgemist.
One thing that you might want to try is, I think it was, let's see, let's take the delay example. Instead of here in the creating the tone, instead of changing this frequency directly in this keyboard function, you might want to slowly interpolate this frequency as well. So let's use this current frequency. This is the starting value, and every time we process this loop, we move towards the frequency that we want. So I'm going to push it back here. And here we use now the current frequency. So we interpolate, smoothly go from one frequency to another, and you get this nothing. Let's use a smaller number here. There's a slight change in the sound, but you might. But if you make it even smaller, you hear the slide here now. So this might give you more ideas that you don't have to jump from one frequency to the next. You can kind of make it even smoother, or like do even this. Okay. Anyways, I think we can continue to creating music. So one of the first things that we may want to try is, instead of playing a single tone, we may want to play multiple tones. So here we have an array for multiple notes, and we can, instead of changing a frequency of an existing note, we add another note to the mix. So we kind of add all of these different functions together into the buffer. So essentially what will happen is that we have, let's say, one sine wave, another like higher one, and then we add these together to get this like mix of those sounds. So, and it sounds like this. And now we have multiple notes. And here we can see that it's not a regular sine wave anymore. It's a mix of staggering sine waves. So, and when you look at this frequency spectrum, you should be kind of somewhat see that there are multiple things. So to create this, essentially this mix of things, we add together all those, the sound from all the different notes, And we also remove those notes that we aren't playing anymore. Otherwise, when we don't do it, we eventually start seeing this, the amount of notes playing together keeps increasing. So currently we don't have a problem with this, but at like 1,000 notes we start to get those glitches that I showed you previously, that we don't have enough time to generate the audio. So this way we can combine different notes. What's even better is that we could create notes automatically, so we don't have to press any buttons. So here is an example how to create usual scales kind of thing. So here we have defined the scales, C major, and now because the notes are in exponential form, which means that, for example, A is 220 Hertz, an octave above it is 440, and an octave above it is multiplied by 2, so it kind of multiplies by 2, so it's a power kind of plot, so it's not linear in that sense. So to get the actual frequency, we need to calculate this. We have, let's say we have this bass note, this is our 0th tone, and here we use this I, the index, into the scales, divided by 12, because there are 12 notes. So we have this, when we reach 12, then this is 1, so this becomes 2, and this is like the next octave. So that way we can create notes based on some value. Okay, so we take the index of the key and we can create some random note. And but we don't want to press buttons. This isn't a game. So we can make the computer do that for us. So here we have this thing that every 0.2 seconds it plays a note. And we can of course change the note that it plays here. Or we can even try something crazier, like some okay, so this way we can create start creating music actually, when you know how to do it, but effectively the principle is the same. We create multiple sounds and add them together to create one sound, and eventually when you keep adding things to it, you might reach a thing that's called a tracker. So here we add all those ideas that we implemented or discussed together and define this song here, where each track here represents a different instrument. So we create a different note based on when we are like moving through these. And of course we can add effects to it and kind of do different things that we want. So, and we might get so anyways, oh, and And let's add all the effects as well. So, and now you can play with these as well and try to come up with something cool. But presentation-wise, this is pretty much it. There are, of course, if you don't like writing your own audio stuff, or like you like playing more of the music parts, then there are things like SonicPy that are more friendlier interfaces than code, and you can kind of use existing samples to play notes and different things, and so you don't have to write everything yourself, but it's cool if you know what goes on in the guts of the audio system.
Is this JavaScript examples that you showed us here same? It's the core of audio web API.
Yes, I'm using audio web API to like send the data to the sound card, but I'm just using that to send the data to the audio card.
The Google has this web audio API that's basically all this stuff. Really
oh yeah, there's lots of tons of libraries that you can use, so you don't have to write it yourself. But it's really fun to play around with these different effects and come up with your own solutions to things, and do something that somebody hasn't done before, effectively. So, I guess, thank you. And you can keep playing and ask me questions, and the presentation ends here. Any questions? Nope.